So in today's lecture, we're going to go over an approximating method of solving ordinary differential equations. It is the only numerical method we are going to deal with when we try to solve a differential equation. For the most part, we're going to focus on differential equations that can be solved, but it's important to know that most of these equations cannot be solved. So there is an entire branch of mathematical theory, which is numerical analysis, that deals with various methods of approximating solutions of differential equations when an exact method cannot be used. So the method that we're going to focus on, the so-called Euler method, starts with a very simple idea, namely that the derivative can be approximated by a difference quotient. So the type of problem we're going to deal with is an initial value problem. So let's say dy dt, a first order ODE in the standard form, is given together with an initial condition. So let's say y of t naught equals y naught. Remember, in most of the so this is an initial value problem. Remember, in most of the problems, what t naught is equal to 0, right? I mean the initial time. So from calculus 1, remember that dy dt, the derivative of any function with respect to t, is actually the limit of the difference quotient y of t plus h minus y of t over h. So in other words, the limit of the difference quotient as h goes to 0 is the derivative at the point t. So that means if I actually drop the limit sign, I can put the equal sign between these two if h is small enough. So I mean, in other words, I can approximate the derivative with the difference quotient itself. So you could say that y of t plus h minus y of t divided by h is approximately equal to the derivative of the function if h is small. On the other hand, we know that dy dt is my f of ty, right? So f of ty is the entire right hand side of the ODE, but that replaces the derivative. Okay, so that means dy dt can be replaced by f of ty. So if I look at the left and the right side of this equality, you notice that I could actually figure out how to compute a point at a later time if I know the previous point. So let's actually rewrite this equality a little bit better without any fraction. So let's actually multiply by h both sides to move it from left to right, and then later on add y of t. So if we do that, then this equality becomes y of t plus h equals, or approximately equal to be more precise, y of t plus h times f of ty. So this is the so-called Euler formula, and we're going to use this repeatedly to approximate points of the solution to the ODE. So the main idea is that if I give you a point ty, so if I start with the point t and y of t, right? So y at the point at the time point t, then via this formula we can compute a later time point t plus h, y of t plus h. Right, so I mean, we just add h to the time value and then we compute y of t plus h via this formula. So in order to write this whole thing in a better format, we can actually denote these time points, I mean these points we're going to produce with this approximated method, with an index, like t naught y naught will be my starting point, and then t1 y1 will be the next point, and so on and so forth. I know this is a little bit vague at this point, but once we get to the actual example, you'll see it's actually very simple algorithm. So it's an algorithm, in fact, right? So, I mean, the formula also is given in the formula sheet, as you will notice when you look at the formula sheet on Blackboard. So this formula, this recurrence formula, can be written as a recursion in the following way. So the so-called Euler formula, basically it's an algorithm that gives you a point based on the previous value of that point on the solution. So yn plus 1 equals yn plus h times f of t and yn, and tn plus 1 equals tn plus h. So t and yn is the current point, so to speak, and then you're going to obtain the second point by plugging in the current point on the right hand side. So for example, if I know the initial point t naught y naught, then I can plug it in on the right hand side and I can find the next point t1 y1. Then I can plug in this point on the right side and that gives me t2 y2, and I can keep on going on for as long as I want. So I mean the algorithm doesn't have any predetermined stopping point. You just can keep on generating the points on the solution until you're satisfied with the solution that you want to generate. So obviously the smaller h the better. In fact, let's write here as a remark. The smaller h the better. But of course the drawback is that if h is small, then you have to generate lots of points to fill in the solution over a certain domain. Obviously most of the time the computer will do that for you. So let's actually go on with an example. So let's say my initial value problem is y prime equals, let's see, I have an example here, t minus y, and then y of 0 equals 2, let's say the initial point. So you get to decide actually what the value of h is. Some problems will mention that for you, but you could also pick it yourself. Remember, the bigger the value of h, the worse the approximation is, right? So you want h to be as small as possible. Let's pick 0.5, which is actually still big, but it'll make it easier to compute the values right now. Normally h should be much smaller than that. So the time values, you can fill in those first, and in fact the easiest thing is to actually arrange your values in a table with 2 rows like this. So you're going to start with the initial point t naught y naught, leave some room for the actual values. So this is going to be the initial t is 0, and the initial value of y is 2 as well, right? So y of 0 equals 2 means t naught is 0, y naught is 2. Then remember the time step h that separates the time points is 0.5, right? So you could actually fill in the time row right away, right? So I mean t1 will be the previous t plus 0.5. So 0 plus 0.5 equals 0.5. And then t2, previous time value t1 plus another 0.5. So that gives me 1. t3, it's t2 plus 0.5, that gives me 1.5, and let's do one more. t4 is going to be t3 plus 0.5, which is actually 2.0. So you can do this actually in your mind, because you keep on adding 0.5 to the previous time value. So just fill in these values here: 0.5, 1.0, 1.5, 2.0. So this is t1, t2, t3, and t4. And underneath, we're going to put the values of y's: y1, y2, y3, y4. So the y values, of course, will be generated using this formula. Now, one thing to keep in mind, people sometimes get confused on this one. What constitutes f of t and yn? So remember, f of t and yn is nothing but the right hand side of the ODE. So take a look at this. T minus y is the right hand side of the ODE. So that means in my particular problem, f of ty is t minus y. So of course, f of tn yn is equal to tn minus yn. And let's update these values as well, right? So that means the Euler formula, and in fact, let's actually put it here so we have enough room. The Euler formula reads in your case yn plus 1 equals yn plus 0.5, right? Because that's your h value. F of tn yn, which is tn minus yn. Right, so you basically write the formula with your value of h, the value of h that you picked in the problem, and whatever the right hand side is, apply the t and yn, right? So t minus y, that means tn minus yn. So now you're going to repeat this, you're going to apply this formula repeatedly to compute y1, y2, y3, y4. So for example, to compute y1, that means n is 0 on the right hand side, so I'm going to plug in the previous point t naught, y naught. So that means y naught plus 0.5 t naught minus y naught. What does that mean? That means in my case y naught is 2 plus 0.5 t naught is 0 minus 2. You can use the calculator to compute this, but this will give you what is it, 1, right? Yes, so I'll give you 1, and you can write it in the table right away here. Then you compute the second one. So notice now you're going to replace the right hand side of the Euler formula with the next pair, 0.5 and 1. So here we're going to have y1 plus 0.5 t1 minus y1. Y1 is 1, 0.5 t1, 0.5 minus 1, and that gives you, again, using the calculator, that gives you 0.75. 0.75, let's write it here. And then y3, previous value, y1 is 0.75, I mean y2, sorry, you plug in y2, t2, and then plus 0.5, 1.0 minus 0.75. That's 0.875. There you go. So 0.875. And by the same token, y4 equals the previous point, 1.5, I mean, sorry, 0.875, right? Because you plug in y value here, right? So yn. So 0.875 plus 0.5, 1.5 minus 0.875. And again, using the calculator, this should be 1.1875. 1.1875. So make sure you compute these values yourself with the calculator. It's not difficult at all. Probably that's one of the easiest lessons in this entire class. Just make sure you understand how the algorithm works. So again, to actually visualize what goes on, imagine that the real solution, starting at the point t naught, y naught, looks like that. So suppose this is the actual solution, y with respect to t, which presumably you cannot determine. And the Euler method basically approximates the solution at various points. So let's say the h value localizes some points here, on the timeline, but the approximated values are somewhere here, right? So ideally, if h is small enough, you get essentially a bunch of approximating values of y as close as possible to the real solution. Now, of course, if h is big, it's too big, then the error could be quite huge. I mean, the approximated value could be here, right, like that, and then the real value over here. So you always run the risk of having too much of an error of approximation if h is if h is too big. So we're going to have a short part, short second part of today's lecture. I just want to go over one more example, just to make sure people understand how to plug in these values when we use the Euler method. Once again, remember, this is in the formula sheet, so you don't have to memorize it. Just make sure you know how to use it.